the typical inner product is defined in the following way. The inner product between functions f and g is the integral from -1 to 1 of f times g with respect to x. This is not the only inner product. Inner product will have a more general definition we'll talk about here in a second, but for our purposes, this is the most important one. And sometimes this is called like the standard inner product, sometimes this is called the canonical inner product, but it's a special thing. So given the functions f and g, calculate their inner product. We would say the inner product of f and g is the integral from -1 to 1 of the absolute value of x times x squared plus 1 with respect to x. And these are both even functions. So what I can do is I can just do this. This is because the integrand here is even. I don't remember if it was this class or if it was Calculus 3 that I went on a long rant about even and odd functions. Is that here or is that Cal 3? That was Cal 3? Okay. So, have you guys ever heard of even and odd functions? Okay, so do I even need to, does that make sense to everybody? Do I need to talk about even and odd functions?
I think you should talk about it. I definitely heard it, but I forgot what it meant.
Okay. I might as well. Let's go ahead and just talk about even and odd functions. A function is even if plugging in a negative argument is the same thing as plugging in a positive argument. That's what makes a function even. So, for example, x squared is even because if I plug in a positive or a negative, I get the same output. I don't know if you realize this, but cosine is an even function. Anytime I have any old polynomial that has only even powers of x, then the polynomial is an even function. There are lots of ways to make even functions. Like, for example, e to the x is not an even function because e to the x is not the same as e to the negative x. But I can totally make this even if I just go boop, right? Because x squared is even, and if I'm composing any function with an even function on the inside, it's going to make the whole function even. You'll also notice, let me give you the definition of odd function. A function is odd if f of negative x is equal to negative f of x. For example, x cubed is odd because if I take -2 cubed, it's -8. If I take 2 cubed, it's 8. So putting a negative on the argument just makes the whole thing negative, makes the output negative. Sine is an odd function. Tangent is an odd function. Arctangent is an odd function. anytime I've got some polynomial that has only odd powers of x, that would be an odd function because that has only odd powers of x. When I have an odd polynomial, by the way, I cannot add, in fact, any odd function, I can't add a constant term. You can't add a constant on the integral, break the odd symmetry. You can add constant terms if I have an even function, like look at this plus 15, it's still even, but I couldn't add a plus 15 here because it would not work. It would not remain an odd function. So constant terms are not allowed for odd functions. Constant terms are allowed for even functions. It's a little bit harder to make odd functions. But if I were to have an even function times an odd function, what I always get out is an odd function. In fact, if I had cosine of x, which is even, times sine of x, which is odd, that's going to be an odd function. Every time you have even times odd, you get odd. Yeah. Yeah. But if I have, on the other hand, an odd function times an odd function, like sine times sine, or if I have an odd function times an odd function like sine times arctangent, that would be an even function. Because like odd times odd gives me even. So the reason we're talking about this right now is because for all even functions, if I have an integral with a negative lower bound and the same absolute value, but the positive upper bound, right? So that the bounds are equal but opposite in sign. And then I've got this even function f. That's always equal to just 2 times the integral from 0 to the upper bound of that even function. Because what the even function is saying is, we don't care whether we're talking about the left side of the y-axis or the right side of the y-axis. You get the same picture. It has like bilateral symmetry, like cosine has bilateral symmetry. And so if I'm integrating in this direction or I'm integrating in this direction, who cares? I'm going to get the same answer. So rather than going in both directions, the left and the right, we'll just go in one of the directions and we multiply it by 2. For all odd functions, if I have an integral from some negative lower bound to some positive upper bound, and they're the same bound, but just opposite in sign, the value of this integral is 0. Because the deal with odd functions is not that they're the same on both sides, but that they're opposite on both sides. So as I go to the right and I go to the left, I'm getting the same integral, but with opposite plus or minus sign. When I add them together, they cancel out. Even and oddness is something I love to talk about at the start of Calculus 2. Because what you find is whenever you take the Maclaurin series of any analytic function, like sine, tangent, arctangent, blah, 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 the Maclaurin series of an odd function will only contain odd powers of x. And the Maclaurin series of an even function will only contain even powers of x. So even and odds are really important in math theory, but also that's what I'm doing right here. It's making this integral easier for me because rather than having to stress out about the absolute value, I just think, well, the absolute value, it's an even function because it's symmetric on both sides of the y-axis. And obviously, if I plug in a negative x, it's the same as plugging in a positive x for the absolute value. So that's an even function. I know this is an even function because it's an even power of x plus a constant. And then if I multiply 2 even functions together, I get another even function. No, sorry. What did I say? If I multiply two even functions together, I get another even function. That's true. This is not what I get if I multiply absolute value of x times x squared plus 1. But if I'm only integrating from 0 to 1, then I can replace the x with the absolute value of x with just an x. Okay, so that's the full explanation. Here's this, and let's take the antiderivative. Plug in the 0, plug in the 1, and we get 1/4 plus 1/2. That's 3/4 times 2, which is 3/2. That's their inner product. Questions so far? Okay. All right, new functions. We're going to calculate the inner product of these guys. Here's the inner product of f and g. It's the integral from -1 to 1 of sine times cosine. So, is sine even or odd? Odd? Is cosine even or odd? Even. So what about sine times cosine? Is that going to be even or odd? Odd. So what's this integral? 0. So the inner product between sine and cosine is 0. Okay, new definition. We say that two functions are orthogonal to each other if their inner product is 0. In Calculus 3, at the beginning of the semester, we said that two vectors were orthogonal to each other if their dot product was equal to 0. The dot product is a type of inner product in math, but this is a different kind of inner product. We still use the word orthogonal to mean the same thing. We just mean that the inner product is 0 for orthogonal functions. Okay, so if I ask you, show that the following functions are orthogonal, or show that the following functions are not orthogonal, or determine whether they're orthogonal, all you have to do is take the inner product. And so these are not orthogonal because the inner product of these functions was 3/2. These are orthogonal because their inner product was 0. What about these? Let's take the inner product. Is x to the 4th even or odd? Even? Is tangent even or odd? Odd. So odd times even is odd. So this is 0. So yes, these are orthogonal. Does everything make sense so far? Question?
Are the bounds always -1 and 1?
For this inner product, whenever I say the typical inner product, then yeah, the bounds will be -1 and 1. Okay, so I'm not going to be able to pronounce this name. It's very French, but I'll try. The Legendre polynomials are an infinite set of polynomials. There's one for every degree. So if you say, for example, the degree 3 Legendre polynomial is specific, it's unique. There's only one of the degree 3s. These polynomials are an infinite set, and the way we define them is that we say they're mutually orthogonal to each other. So any two polynomials you pick from this set, they're going to be orthogonal to each other. And every one of these polynomials, if I plug in x equals 1, I should get the value 1 for the value of the polynomial. So if n is equal to 0, I have a degree 0 polynomial. What does this have to be? A constant. What constant?
C. 1.
1. It has to be the constant 1, so I can satisfy that condition. Okay, if n is equal to 1 now, this is a degree 1 polynomial. I've got two things I can mess with. I've got two knobs I can turn. I can either change the slope or change the y-intercept, but I have to have a polynomial that looks like this in the end. And what I know about this polynomial is that when I plug in x equals 1, I better get 1 out. And when I take the inner product between this polynomial, call it mx plus b, and the previous polynomial, which is the number 1, that has to be 0. Why? Because these have to be mutually orthogonal under the typical inner product. So that means I should be able to take the inner product of this polynomial and that polynomial, and it should give me a 0. In order for this integral to be 0, with bounds -1, +1, this integrand needs to be odd. Thank you. It needs to be odd, so I can't have a little constant. I can't have a little plus b there, or else it's going to mess up the oddness, right? So forget about the plus b. It's going to have to be something like mx. And if this is mx, what does m have to be so that when x is equal to 1, the polynomial is equal to 1? 1. So the Legendre polynomial of degree 1 is just x. Maybe things will get a little more interesting, a little spicier with degree 2. So what do I know about degree 2? I have to be able to plug in x equals 1 and get out 1. And I also need to be able to take the integral from -1 to 1 of p2 times p0 and get 0. And I also have to be able to take the integral from -1 to 1 of p2 p1 and get 0. Because these should all be orthogonal to each other, right? And knowing that this is a second degree polynomial, this is going to look something like ax squared plus bx plus c. So this integral becomes the integral from -1 to 1 of ax squared plus bx plus c times 1. And that has to be 0. Again, to make it equal to 0, this integrand needs to be odd, which means that I take it back. Does it have to be odd? If the integrand is odd, it definitely makes the integral 0, right? But actually the converse isn't necessarily true. You could still have this integral be equal to 0 even if the integrand is not odd. So I was jumping ahead of myself a little bit. Let's work it out. If I go ahead and take the antiderivative, I get 1/3 ax cubed plus 1/2 bx squared plus cx. And I'm plugging in -1 and I'm plugging in +1. And I want that to be eventually equal to 0. Okay? So if I plug in -1 and I plug in -1, the odd powers of x are going to cancel each other out. And the even powers of x are going to be essentially doubled. So this is going to be b equals 0, right? Does everyone agree? I don't know why you would agree with that. That's totally wrong. No, that's wrong. I forgot to subtract. Because we're plugging in the +1, and then we subtract what we get when I plug in the -1. Okay, now I plug in the +1 and I subtract what I get when I plug in the -1. Now I plug in the +1 and I subtract what I get when I plug in the -1. So really, this is going to be 2/3 a plus 2c equals 0. That's what we're really learning from this. If I'm just a little bit more careful and I slow down and then think through it. Okay, now does everybody agree with me? Does that make sense? Okay. Let's see what else we can learn. Like from here. If I take this, it'll be the integral from -1 to 1 of ax squared plus bx plus c times x dx has to be equal to 0. And then that is, go ahead and take the antiderivative here. So it's ax cubed, and then we take the antiderivative, it's going to be 1/4 ax to the 4th power. Then I've got bx squared. So after the antiderivative, it'll be 1/3 bx to the 3rd power. And I've got cx, so in the antiderivative, it'll be 1/2 cx squared. And when I plug in 1 and -1, that should give me 0. Okay. Now, if I plug in the 1 and I plug in the -1 and I subtract what I get, it turns out the even powers of x are going to go away. So what I'm really interested in then is that 2/3 b should be equal to 0. Because 1 to the 4th and -1 to the 4th are both 1, and then I subtract those, so the first term goes away. 1 squared and -1 squared are both 1, but I'm going to subtract them, so the third term goes away. And then this would be kind of like a 1/3 b minus a -1/3 b, so it gives me 2/3 b, and that has to be equal to 0. Okay, so what this P2 of x then is going to be ax squared plus c, where I have this relation between a and c, and I also know that if I plug in x equals 1, I should get 1, right? So a plus c has to be 1, because if I plug in x equals 1, this becomes a plus c, and that needs to be equal to 1. So I've got a system of 2 equations with 2 unknowns. Here's one equation, here's the other. And I'm going to write them one on top of the other so you can see. All right, a plus c equals 1, and 2/3 a plus 2c is equal to 0. Let me take the first equation and multiply it by a -2 to get like -2a minus 2c equals -2. And then I'll add these. So that way I get -4/3 a, the c's cancel, equals -2. Divide both sides by -2. So a equals 3/2. And if a is equal to 3/2, c needs to be equal to what? -1/2. So we're ready to write down p2 of x is equal to 3/2 x squared minus 1/2. That has to be the Legendre polynomial of degree 2. The next thing I'm going to do is I'm going to find the Legendre polynomial of degree 3, and there's going to be 4 little hints that I can use to figure this out. Number 1, if I take the inner product between the polynomial of degree 3 and the polynomial of degree 0, that inner product has to be 0, because they have to be orthogonal. If I take the inner product between the Legendre polynomial of degree 3 and degree 1, that inner product has to be 0. And if I take the inner product between the Legendre polynomial of degree 3 and the Legendre polynomial of degree 2, that inner product has to be 0. And then lastly, p3 of 1 has to equal 1. So I got 4 little clues, and that's important because for a degree 3 polynomial, there's 4 coefficients, right? There's a constant, and then there's the 3 coefficients on your remaining terms. So let me clear off some room here. We can work that part of it. So suppose we want the 3rd degree. We figure out what this is. It's going to be something like c3x cubed plus c2x squared plus c1x plus c0. We just got to figure out what all those coefficients are. We've got to figure out what c3 is, what c2 is, what c1 is, what is c0, and then we'll have it. They need like a big eraser for when you have a lot to erase. This tiny little eraser. Whew, okay. Now, That means let's take the integral from -1 to 1 of this whole thing, c3x3 plus c2x2 plus c1x1 plus c0 times the Legendre polynomial of degree 0, which is 1 dx. And so then we're going to have all of the odd powers of x go away, right? Because in the integral from -1 to 1, they all are all equal to 0 anyways. What we care about is what happens to all the even powers of x, like 1/3 c2x to the third, and then the other even power c0x. And so obviously plugging in the positive one and subtracting what I get if I plug in the negative one is just going to double these. And that has to be equal to 0. Next up, we take the inner product between this Legendre polynomial of degree 3 and next the Legendre polynomial of degree 1. And whenever I multiply through by the x, now I'll have c3x to the fourth, which is 1/4 c3x to the fourth. No, x to the, sorry, fifth. My bad. And then that's odd, so it goes to 0. This one is not. It's going to be c1x squared, or after the antiderivative, 1/3 c1x cubed. And that becomes odd, so it goes away. So you take this, you plug in the 1, you plug in the -1, you get equal but opposite, and then so it's kind of like doubling this, and so I get 2/5 c3 plus 2/3 c1, and that adds up to give me 0. The next thing I would do is I would take the inner product between this Legendre polynomial of degree 3 and the Legendre polynomial of degree 2, which is 3/2 x squared minus 1/2, and then make sure that's set equal to 0. And then the last thing I would do is I would take the Legendre polynomial of degree 3, plug in x equals 1, and make sure that it gives me 1. At the end. So what happens in red, I would have to multiply in the integrand and then take all the antiderivatives using the power rule, and then plug in the upper bound and the lower bound and subtract. And then I would get another one of these equations. And so altogether I'm going to have 1, 2, 3, 4 linear constraint equations. I'm going to have 4 unknown variables, C3, C2, C1, C0. And with 4 equations and 4 unknowns, you should be able to solve for the unknowns, and then you would learn, oh, that's the Legendre polynomial of degree 3. So it's kind of a painful process, and it only gets more painful the larger the degree of the polynomial. But there's actually smarter ways to do this. If you go to Wikipedia, these polynomials have their own Wikipedia page, naturally. And the first thing it mentions is that, yeah, these are orthogonal, very important to know. And they also have different ways of figuring these out. There's smart people that have defined this as the, answer to this generating function. This is also the solution to this differential equation. There's some formulas for constructing these called the Rodriguez formulas. And you can double check our work too and just make sure, do we get the degree 1, degree 2, degree 3 polynomials correct? Yeah? I think we did. Look, you can even see a pretty graph here. A graph from -1 to 1, and notice all of these polynomials are equal to 1 here, as they should be. That's the idea. We'll explain this. You're probably thinking this is crazy. Next Monday, we'll talk about why this is important for numerical analysis. But for today, let's just roll with it for now. So the Legendre polynomial of degree whatever, right, degree 5, degree 50, degree 500, is orthogonal to every polynomial with degree less than or equal to its own degree, right? What this means is if I have the Legendre polynomial of degree 5, that's orthogonal to this polynomial. And any other polynomial you can come up with degree 0, 1, 2, 3, or 4. It's kind of neat. But if you wonder why, like why could that possibly be true? Because any polynomial of degree less than or equal to n minus 1 can be constructed from a linear combination of the first n Legendre polynomials. That is 0, 1, 2, 3, dot, 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 n minus 1. And the procedure for constructing that would look like this. So first, choose some multiple I'll call it n for multiple of the 4th degree Legendre polynomial, so that the leading coefficients match. In our case, in our little example, where n is equal to 5, what I would do is I would look at the 4th degree Legendre polynomial, and I would say that leading coefficient is 35/8. Okay? 35/8. And what I want the leading coefficient to be is 700, right? And so I would have to do a multiple 700 divided by 35/8. Because that way I can get the right leading coefficient, the number 700, if I start off with M4 P4 of x. Then choose another multiple such that I could multiply the third degree Legendre polynomial times m3 and get the right coefficient on the x cubed term. Okay, because if I multiply the fourth degree Legendre polynomial by this crazy number, that's going to be something, right? But what I really want that to be is 1.5 or negative 1.5. So how do I make it be negative 1.5? Well, I could add some multiple times the third degree Legendre polynomial until I get exactly the coefficient that I want. And it doesn't change this coefficient 700 because this is only a degree 3 polynomial. Okay, in the next step, I would already have some kind of coefficient on an x squared term, but I want that coefficient to be 0, so I could choose the right multiple to add that multiple times the second degree Legendre polynomial to 0 it out, and then I would already have some coefficient on the x term, but I could correct that until the coefficient is the number 1 by adding some multiple of the first degree Legendre polynomial. And then I would just have a constant term. If I want the constant term to be exactly negative 17, I just add some multiple of the degree 0 Legendre polynomial. And so I can express any polynomial as a linear combination of Legendre polynomials up to that degree. And so since the polynomial I'm talking about, let's call it Q. Since this is just a linear combination of the Legendre polynomials, oops, it's supposed to be plus. And since that's orthogonal, what happens is I go to take the inner product between P5 and Q4, right? But I can go ahead and break that inner product integral into the inner products of P5, P4 times a constant M4 plus the inner product of P5, P3 times that constant multiple, and so on. Well, first you can take a constant out of an integral, and then second, these Legendre polynomials are orthogonal to each other by definition, and so all of these inner products are 0. So I've got 0 plus 0 plus 0 plus dot dot dot, and that's orthogonal. So Legendre polynomials are nice because they're not just orthogonal to each other. Every Legendre polynomial is orthogonal to every polynomial that has a degree less than its degree. It's pretty cool. Pretty nice property to have. Okay, so this is, like I said, there's more than one inner product. We're talking about the typical inner product, but any inner product, and there's you can define an infinite number of different inner products, but this is what it means to be an inner product in mathematics. It has to be symmetric, which means if I want the inner product of f and g, that's equal to the inner product of g and f. It doesn't matter the order. This is a commutative operation. Inner product has to be linear, And linear means that it has additivity and homogeneity. Those are fancy words that mean if I'm adding AF plus BG, well then that should be equal to the inner product of AF and H plus the inner product of BG and H. And then homogeneity means if I've got a constant A times F, I should be able to pull that out of the inner product. If I've got a constant B times G, I should be able to pull the constant outside of the inner product. And so together, those two properties together are known as linearity. And then positive definiteness. So if I take a function's inner product with itself, it has to be a positive real number. It has to be strictly greater than 0. And that's what we mean by positive definiteness. So if you took linear algebra, think about the dot product. If you took calculus 3, think about the dot product. The dot product is symmetric, it's linear, it's positive definite. So it fits the same description. If you've got something that says show the following operation is an inner product, this is easier than you think it is. You just have to remember what are those three properties. Symmetric, right? And say, this is symmetric because the integral from -1 to 1 of f of x times g of x is equal to the integral from -1 to 1 of g of x times f of x. Number 2, what was the second property called? Linearity. This is linear because if I were to have some inner product of, let me see what I was calling it. You don't have to use the same symbols as me, but I was calling it AF plus BGH. That would be the integral from -1 to 1 of a times f of x plus b times g of x times h of x dx. And that would be equal to a times f of x h of x dx plus b, integral from -1 to 1, of g of x h of x dx. And that would be a times the inner product between f and h plus b times the inner product between g and h. So we've checked to make sure that it's symmetric. We've checked to make sure that it's linear. What was the third thing it has to be? Positive definite. And we know this is positive definite because if I take the inner product of a function with itself, that would look like the integral from -1 to 1 of f of x times f of x, which would be the integral from -1 to 1 of f of x squared and since f is real valued as a function, we get only a positive integrand because it's squared, or I should say the integrand is at least greater than or equal to 0 everywhere. So as long as the function f is not identically 0, then it's positive definite. As long as f of x is not the constant function 0, then this inner product of f with itself is greater than 0. And so we say that it's positive definite as an inner product. And so don't overthink these. It's really not that hard. This type of question, I really just want you to say, listen, I remember the definite of an inner product means it's symmetric, linear, and positive definite. I know what those words mean, and I can demonstrate that I know what these words mean by writing them down and plugging them in. Okay? Prove the following trig identity. Well, for one thing, I think we maybe already proved the identity for cosine of alpha plus beta. My problem is I can't remember it. And so what do I do if I can't remember something?
Redo it?
I prove it from scratch again. So here's cosine plus I sine. And on this side, it's going to be cosine alpha plus I sine alpha times cosine beta plus I sine beta. And then if I ignore the imaginary parts and I just take the real parts, we get cosine alpha cosine beta imaginary, imaginary, and then minus sine alpha sine beta. Okay, very good. And so what I'm trying to prove is this thing up here typed out. Cosine alpha cosine beta is equal to 1/2 cosine alpha plus beta plus cosine alpha minus beta. The other thing looks like I'm going to need is cosine alpha minus beta. And I can get this if I just replace this beta with a negative beta, and we see what happens. So I'm going to end up with cosine alpha cosine negative beta. Do you guys know what is cosine negative beta? Yeah, the same thing as cosine beta. So that doesn't change. Over here, what is sine of negative beta? Negative sine beta. So over here, this becomes a plus sign, since two negatives make a positive. And voila. So what's happening on the right side here? I'm taking cosine of alpha plus beta plus cosine of alpha minus beta. I'm adding those together. What would it look like if I add these together? Well, this is the same, so that will be doubled. But these...
Cancel out.
Your name's like Maggie or Maddie or something, right? You're not my student. I don't know your name. What is it? Alyssa. Is there a Maggie or a Maddie that hangs out upstairs?
Yeah.
A Maddie.
I've talked to you like 700 times.
You never told me your name.
Yes, I have. We introduced herself.
She came into classes with me the other day, and she introduced herself.
Okay,
I've
sorry.
introduced myself
I wasn't paying
3
attention.
times.
I'm sorry.
That's fine. I don't care.
Okay, so we add these together. We're going to get 2 cosine alpha cosine beta. Then look, I'm multiplying by 1/2. 1/2 times 2 cosine alpha cosine beta gives me 1 cosine alpha cosine beta. Everyone buys it? Are you convinced, Kevin? Okay. I have Kevin's approval. So we can move on. Now, we were talking about this last time. And I kind of got stumped. This was the cliffhanger we left on. It's like, given the... Yeah.
Okay, cool.
And so here we are. We're doing the inner product of cosine mx and cosine nx. So we're looking at an integral from 0 to pi of cosine mx cosine nx dx. And this is where we were like, crap, what do we do? But what we're going to do is we're going to use the identity that we just showed, right? We're going to use cosine of mx times cosine of nx equals 1/2 cosine of blah, blah, blah. And you added them up. So here we try. Here we go. Using that identity, this becomes 1/2 cosine of mx plus nx plus cosine of mx minus nx. Double check I'd put in right. Yeah. So if m is equal to n, then this is cosine of 2nx plus cosine of 0. And I've said that m and n have to be positive integers, or non-negative integers at least. So if those are integers, then this is an even integer times x. So let's see. Let's take some antiderivatives. Antiderivative of cosine would be the antiderivative would be sine. The derivative would be negative sine. So we've got sine of 2nx, and we divide by 2n, right? Put that somewhere. And then plus 1, the antiderivative of 1 is x from 0 to pi. So whether I plug in the 0, you know, sine of 0 is 1, 0. And sine of an even integer times pi is 0. Yeah, sine of 0 at all integers times pi. Plus this, and this is just pi. So it looks like we're sitting at something like 4 over, no, sorry, pi over 4n. Except I don't think that's right. I wonder if I made a mistake somewhere. Do you guys see a mistake anywhere?
Can you factor out the 1 over 2n if it's only attached to the sine term? Yeah.
No. You're right. So that's a mistake. But I don't think that really saves us. I think you still get the same answer, don't you?
Yeah.
Because if you plug in... Oh, no, you don't get the same answer. Sorry. What is the answer? Pi over 2. Yeah, because the signs are always 0. Whether you plug in the pi or you plug in the 0, the signs are 0. The x becomes a pi over 2. But that's only if m is equal to n. If m is equal to n, then this inner product between cosine of mx and cosine of nx is pi over 2 if m is equal to n. But what if m is not equal to n? Let's do that case. If m is not equal to n, then this is going to be 1/2 times the integral from 0 to pi of cosine mx minus nx, right? No, plus. plus cosine of mx minus nx dx. Or I could factor out the x and call it m plus n times x. And then I could factor out the x and call it m minus n. What's my antiderivative of cosine here? Sine and 1 over m minus n sine of m minus n x okay, this time m and n are both integers, right? Positive integers. So whether I add them together or I subtract them, I'm going to get a positive integer. And I'm not going to get 0 because we said that m and n are not the same positive integer. So no matter what, I get something that's not 0 here and here and here and here. X, if I plug in 0, is going to give me sine of 0. That's 0. So I don't have to worry about the lower bound. Everything gets to be 0. When I plug in x equals pi for the upper bound, I've got sine of an integer times pi, which is 0. And then sine of an integer times pi, which is 0. Making sure you're paying attention here. So there you go. If the integers m and n are not exactly the same number, then the inner product between the cosines is 0. Okay. Now that we know that, now that we've proved this inner product thing, we can finally get ready for where we left off last time. So we said these are the Chebyshev polynomials. There's one polynomial for every degree. And we said these Chebyshev polynomials are mutually orthogonal under the following inner product. M and n are not the same, and they're positive integers. Evaluate the inner product between two Chebyshev polynomials of different degrees. Okay, so my inner product between Tm of x and Tn of x is going to be the integral from -1 to 1 of Tm of x times Tn of x times 1 over square root 1 minus x squared dx. All right, do you remember from last time, what did we do next in this process? Maggie?
Not Maggie.
You're right, no. Whatever. I lived out here going crazy. Like, I don't know, use substitution?
You're right.
What is it actually, use substitution?
It's a use substitution. What's the substitution I'm going to use?
Is it 1 minus x squared?
Well, I guess you're right. If I'm already using the variable x, let's call it x equals cosine theta. But yeah, we are going to make the substitution. And the substitution x equals cosine theta means that the derivative of x with respect to theta is negative sine theta. You didn't give Maggie a chance to get that one. So we've got the integral. This Tm of x is now Tm of cosine theta, and Tm of cosine theta is going to be cosine of m theta because of this definition here. So we write cosine of m theta. This is going to be cosine of n theta. And then this is 1 divided by square root of 1 minus cosine squared theta And then dx is going to get replaced by negative sine theta d theta. The lower bound, -1, is now going to become what? We're going to use this right here to determine when x was equal to -1, what theta is going to make cosine of theta equal to -1? Pi. And then what theta is going to make cosine of theta equal to +1? 0. So those are my new bounds. And now you remember, I think last time we used this little negative sign here to swap the order of the bounds. So I can make that 0 to pi if I take away that negative sign. And then you remember that 1 minus cosine squared is sine squared, right? And the square root of sine squared is sine. And the sine in the numerator cancels the sine in the denominator so that we get this. And since m and n are positive integers, but they're not equal to each other, this is 0. And if the inner product is 0, that means these polynomials are orthogonal.